What's driving this change in demand? Here are some of the results and how those parameters were quantified. Population increases throughout all of the demand scenarios, so this really is a major driver in that future demand. From about 40 million people in 2050 to about 77 million people, so almost double that amount by 2060 under the rapid growth scenario, or about 49 million, adding less than 10 or 23% increase by 2060 under the slow growth scenario. The per capita water use is decreasing across all of the scenarios. It decreases by 7% to a maximum of almost 20% under the enhanced environment scenario. But that decrease in per capita water use is not enough to counteract the population increase. We're also seeing a decrease in irrigated acreage across all of the scenarios. It's fairly small, but nevertheless there is a decrease at a basin-wide level. It's going from about 5.5 million acres, decreasing by at most 4.6 to 4.6 million acres, which is about a 15% decline. And that decline is due in part by two reasons. One, we're seeing an expansion of urban areas, so urban encroachment onto irrigated lands, but also adoption of efficiency technologies that result in more food that can be grown or more crops that can be grown on a smaller area of land. And I do want to caveat that these results are for the basin-wide level. What is provided in that technical C will be how these parameters and demands play out for each one of the 7 basin states and for multiple planning areas throughout those basin states. So as you start to look at some more detail within those planning areas, some of these use types are moving in different directions, but this is a picture of a basin-wide view. So if we bring supply and demand together, as shown in this figure here, we can understand what the future imbalance might be moving forward. So this figure is showing you the data from, in part showing you the data from earlier on in the presentation. There's that historical 10-year running average water supply and water use. And now we've plotted on what the future projections for water demand and water supply look like, again at a 10-year running average. And there's a cloud there because that's the range that we found after quantifying those future scenarios. The darker shaded areas there in between in the two clouds for supply and demand is where the median of those projections lies. And if you compare those two medians out by 2060, you get a roughly 3.2 million acre foot imbalance. Now that can be much more or much less depending on the nature of the particular supply and demand scenario. And as we've noted previously, imbalances have occurred in the past, and it has been our reservoir storage that has allowed us to meet deliveries during this time. And so where we really need to go from here is to understand how this imbalance plays out in terms of its impacts on the resources. Factor in the impacts of reservoirs and factoring in the needs of the various resources across the system. How vulnerable are these resources to imbalances of this magnitude? Okay, I'm going to shift gears now into thinking about different solutions or options and strategies to deal with the imbalances projected in those previous phases. This is detailed in Technical Report F. You'll find quite a lot of information on all the various options that were considered in the study. I'm going to talk you through this really in four parts: the objective, talk about the options that were considered, the characterization of those options, and then how we combine those options into different portfolios. So the objective of the options and strategies was to explore a broad range of options and to group those options into portfolios for resolving future supply and demand imbalances. Because we've demonstrated that we do have a very broad range in terms of future supply and future demand and the imbalances resulting from that future supply and demand, we definitely want to look broadly when we're thinking about options to resolve those imbalances. The study did not intend to result in the selection of any particular portfolio or option. Rather, and again, is to demonstrate a broad range of different options or portfolios that will be effective at resolving those future supply and demand imbalances. So to come up with the ideas that comprise the options and then into the portfolios, we asked the public to submit ideas. And we did so over a 3-month period from November 2011 to February 2012, and over that time we received 160 options. All of these options are included and are reflected in the study. In that technical report F, you will find an appendix that has all of the options as they were submitted and a guide that will help you see how the option got filtered into the various category and ultimately how it was considered in the study. The pie chart here is showing you the distribution of the different types of options. There's 4 major broad categories. The first is called increased supply, and these are really looking at the different options that are bringing more supply into the basin. So increasing the water that is available for use in the basin. This can either be through reuse type activities, desalination, which includes both ocean water, brackish groundwater or agricultural drain water, importation type ideas. So this includes building pipelines to import water from other river basins outside of the Colorado River Basin. Other ideas fall into this category, such as towing icebergs from Alaska. Some of the more far out options are in here as well. There's also watershed management, which includes ideas such as weather modification or cloud seeding. Vegetation management type options are considered increased supply as well. And that came in about 35% of the ideas received. Roughly at about a quarter of the ideas are reduced demand ideas. These are really your M&I conservation and agricultural conservation. There's a few energy use efficiency ideas that fit in here as well. Modify operations. These consist of options that were received that propose changing the operation of various reservoirs, taking down certain dams on the system, using water in a different way through transfers and exchanges, water marketing or water banking. These ideas came in at about 15% of what was received. And about a quarter of the ideas then fit within a category we call governance and implementation. These were ideas that weren't so much focused on resolving that imbalance as they were different types of governance and implementation structures that might be used to implement some of the options. And so these included things like new stakeholder committees formed on the basin. There was population control that fit into this category, as well as reallocation of the allocations in the Colorado River Basin. The way these options were dealt with were to put them into like categories at even a finer level than the 4 major categories discussed here. There was a quantitative analysis that was performed really for the increased supply and reduced demand type options because they were just easier to handle quantitatively. A qualitative discussion was provided for many of the governance implementation and the different modify operation options. However, we did design a conceptual water bank that's included in many of the portfolios. So this figure kind of depicts this concept of how we take the various options that fit into those major categories and filter them or funnel them into finer categories. And the categories shown here do not represent all of the option categories that we considered. But the idea is to, within each one of these categories, develop what we call a representative option. And a representative option is formed by either taking an actual option as it was submitted or from multiple options that came within a category, designing our own representative option to, again, span the range of the ideas within that category. Then we did a characterization of those representative options through a set of criteria. There's a set of 17, a sampling of them are listed here. These include things like quantity of yield, the timing to implement a various option, the technical feasibility, the energy needs associated with that option, the cost both at an annual level and an average annual per acre foot level, any permitting issues and legal and policy considerations associated with that option. This characterization was done at an appraisal level, so it really was a course estimate in many cases. And this characterization was done again through a multi-stakeholder team that thought about all of these options, worked with the consultant team to develop not only numeric characterizations in terms of yield, timing, and cost, but also to apply ratings, A through E, to each one of these characterization criteria. This figure here shows the results of applying those different ratings, A through E, to each one of those representative options. And the representative options is that second column shown there. So for, if we look at reuse, the 3 representative options there is reuse of municipal water, gray water, or industrial water. So A is generally a favorable rating, E is generally a non-favorable rating. The more favorable ratings are in green and the less favorable ratings are in red. And the point to doing all of this was really to build our foundation to express strategies to be able to package these options together. And the acknowledgement is that there's no one option that's going to solve all of the imbalance, and that rather it's going to take a packaging of these options. And the packaging of the options we called in the study portfolios, and these implement a particular strategy, and we use those ratings for the various criteria to express those strategies. We developed 4 different portfolios that are really meant to demonstrate potential ways, but not all of the ways various options could be considered. And this figure here just conceptually shows the idea of building portfolios, and you have a different percentage of each option type that's contributing to that portfolio as you move forward and fill in the projected imbalance. The 4 different portfolios, as I said again, express 4 different strategies. Our portfolios are labeled A, B, C, and D. In portfolio A, this is the least restrictive portfolio, and the strategy here is really to include a very highly inclusive set of different option preferences. And if we look at the schematic, the black line that is the outline of the entire circle is showing you the entire universe of the options considered. So to develop portfolio A, we placed a filter to weed out some of the more kind of extreme ideas, things such as towing icebergs, the ideas that were not technically feasible or extremely costly, provided that type of filter first, and then we came up with portfolio A, and a lot of options are included in this portfolio, and in the next slide we'll look at specifically what options are in these portfolios. Options B and C are expressing 2 different strategies. imbalance. B is really expressing a low risk, high reliability, high certainty in terms of a future water supply in the future. It's focused on ideas that have a high technical feasibility, so are proven to work, and excluding those with high permitting, legal, and policy risks. Portfolio C is more focused on prioritizing the options that have low environmental impacts and low energy needs, and those options that provide long-term flexibility and are adaptable to as we look into the future and we find ourselves in different conditions. These types of options could be adapted to meet those different conditions more. In Portfolio D, we're looking at the most restrictive set of options, and these are options that only meet the criteria set forth in both B and C. And this gives us the smallest set of options and a very restrictive view in terms of what to implement to deal with future water supply needs. So this table here is showing you a summary of the option inclusion across all of the portfolios. You have your option category listed down on the leftmost column, and then again there's your option group or your representative option, and then you have each one of the 4 portfolios and an X in the portfolio if that option was included in that portfolio. If the option is not on this list, the option was not included in any portfolio. So some of the options that are selected that help you understand the different strategies that are reflected in some of these portfolios. One, if we look at dust control, so this is an option under watershed management. This option was included in portfolios A and C. And if you recall, portfolio A is the most inclusive, including all of the options in both B and C. It would make sense that this option is here. Portfolio A, in fact, includes every option on this table. But Portfolio C has this option because it is low environmental impact, low energy needs, and flexible. But it's not a high, it doesn't provide high reliability in terms of the future water supply. And that's why it didn't make the cut to go into Portfolio B. And so if we thought about that characterization criteria, the things such as reliability or technical feasibility, dust control would be one that would score fairly low on that type of criteria. On the other hand, if we look at if we look at Pacific Ocean desalination in California, for example, this shows up in Portfolio B but not in Portfolio C. It got weeded out in Portfolio C due to the energy needs associated with this option and possible permitting issues. In Portfolio B, because the focus is on a reliable and certain water supply, this scored high in terms of reliability and proven technology and technical feasibility. And if you look at Portfolio D, you're again seeing the smallest set of options that have been selected. So with that, we're going to take a break for about 10 minutes. We're going to reconvene at 2 o'clock. We're a little ahead of schedule. And so we are going to reconvene at 2 o'clock. And at that point, Ken and Alan are going to take you through how these portfolios perform and how the different resources are impacted by some of these supply and demand imbalances. So we'll talk to you at 2.